Hello and welcome to our 22-minute webinar, Fast, Simple, Powerful Soft Goods Design. My name is Shyam and I will be your host. Now I'd like to present today's speaker, Ethan Donald. Ethan Donald is the CEO of Tri-D Technologies, a firm whose mission it is to make it faster and less complicated for manufacturers to design and develop products that include composites, industrial fabrics, and technical textiles. Ethan, it's all yours.
Thank you, Shyam. I'd like to take this opportunity to welcome everybody to our webinar today, and thank you for taking an interest in ExactFlat for SolidWorks. We're going to cover two agenda items today. The first will be our workflow, which will give you a broad exposure to ExactFlat. We're going to cover pattern piece creation, 3D to 2D flattening, adding pattern features, nesting, and exporting. And at the end of the workflow, we're going to go back and cover other aspects of the flattening process, which we did not touch on during the first phase. And particularly, we're going to talk a little bit about complex surfaces and flattening complex surfaces. I would encourage every participant out there to ask questions if you have questions along the way. The first part is going to be relatively high level, but it'll give you a flavor for how this work can be done. As Shyam did say, our mission is to make it faster and less complicated to design and develop products that incorporate composites, technical textiles, and industrial fabrics. And without any further delay, let me just get right into it. We are looking at here, in this example, an automotive seat bun. This is the portion of the automotive seat that you sit on. It was modeled in SolidWorks, and you can see that it is comprised of different surface bodies. What we're going to do right now is we're going to convert the surface bodies into pattern pieces. We do this simply by selecting the individual bodies and then clicking on Create Piece. And you can see when the pieces are selected, they become highlighted. And then when they are created, they become transparent and locked for editing. And this is just a fast and simple way to go from CAD geometry, where you may have many fillets or other features associated with your product, and get to the pattern geometry that you desire. It's a pretty quick process. Once we do that, we're going to now convert this to an ExactFlat part. This will take a few seconds as we are creating an index mapping of edge associations here. And when all the edge associations are in place, we'll be prompted to add material or to select material. So we're going to take all these different pattern pieces and we're going to put a material here, let's say leather, and assign it. And there we have it. Now when we did that assignment, what happened is we also attached or associated engineering characteristics and nesting of variables that will be used in a downstream process. The engineering characteristics are particularly relevant for our flattening process, which we're going to show next. We're going to go quickly into our view pattern mode, and you can see we have an initial flat pattern. We're going to lay these pattern pieces out before we go into our flattening. And what we're doing now is we're just going to create a visual layout which is analogous to how these pieces may be sewn together. And to do that in ExactFlat, we just simply click on the edge of a particular pattern piece, and our program will find the adjacent edges and align them with a certain offset, which is defined by the user. And as you can see, we have the ability to walk or place patterns in precision here simply by holding down the mouse button and moving that along a certain edge. And this will take a second to wrap up here, and there you have it. Now we've got a sewing layout. We're going to now move into our flat pattern environment. And what this environment does is it optimizes the fit of a flat pattern. It is designed to flatten complex surfaces. The first part of the process is we're going to create a mesh which is optimized for analysis. The mesh elements are going to be redrawn, and they'll be optimized in such a way that when we do our flattening algorithms run, we will decrease the solve time and increase pattern accuracy. And you can see that it's roughly drawing the mesh elements in proportion to one another such that they're the same size. And it'll just take a second or so. When the meshing process is complete, we simply click Optimize, and it'll go through a process of searching for strain and sag. That's excess material is sag, and strain would be where the pattern pieces are going to have to pull tight. And it's going to try and eliminate them. It's going to try and pinch the strain away, and it's going to relax or add material where there is, it's going to pinch the sag away, and it's going to add material where there's strain. And you can see we've just about got this optimized. This is not very, very difficult geometry here, so it should take a couple more seconds before you've got your flat pieces. But these are flat pieces that you can actually sew back together and put on your physical prototype or your part, and they should be fairly accurately fitting. So let's close out of here. This is the first two aspects of our workflow, and what we have to do first is just rebuild our pattern pieces so that our edge geometry is updated. And this will take a second for us to update the geometry. The next aspect that I'm going to show you is we're going to add some pattern features on here. But before I do that, I just want to talk a little bit about our ExactFlat environment. We're going to click on our model view, and this is the SOLIDWORKS modeling environment. We're going to click on our pattern view, and here you can see that the pattern view is brought up. Now we're going to click on what we call our marker view. And the marker view, you can see, is a nesting environment. We have integrated all three aspects of the workflow such that they are accessible within the same SOLIDWORKS environment. And for those of you who are familiar with this work, using other technologies, this will probably be seen as a very refreshing, welcome addition to how this work can be done, that you can toggle back and forth between the different environments. In starting our patterning features, it's very simple. We click on a primary edge of a piece, and when we click on the primary edge, what happens is the associated edge is highlighted and shown to be connected to the initial edge. So you only have to add the pattern feature to one edge, and then the remaining edges will also be given the same pattern feature. And it's very simple. You click the edge, and you select from our Property Manager page the type of seam that you want, and the program will automatically apply it. I will say that if you look on the left-hand side, as we get to the seam type, these seam types are actually drawn from a database. They are configurable and editable. So if you have certain seam types that are particular to your industry or to your company or to the type of products that you make, you can actually put those in here. And rather than having a very long list that is going to account for every possible variation in the marketplace, we've allowed users to have the ultimate flexibility and edit the seam types that they put on and have them at the top of the list. We're just about done here. We just have a couple of more edges to do. There's 1 and 2, and we'll put another join on here. And that's it. That's basic pattern engineering. We have other pattern engineering features. For example, we can have standard seams, hems, bound edges, raw edges. We can have hardware. You can put markings, drills, or grain lines on a part. But we're going to skip that for now, and we're just going to go into our marker view. And we're going to create a nested file. Now what I'll point out here is you can see that these pieces are overlapping a little bit. That is because we just did put seams on here. So we're going to just reset our initial marker. There it's reset. And what comes up when we first go into our marker view is what's called an auto-generated marker. The auto-generated marker is the marker that is created by default. It is based on settings which are pulled from the database, and these settings are associated with the type of material that we've chosen. So for example, if there's a grain line on a particular material, then that will allow a rotation or not allow a rotation depending on what we have. Other settings that we could edit here are lay rules, which is the type of rotation that would be on a pattern piece. The piece gap, which is the gap between pieces. Edge buffer, how close we want the pieces to be laid on the roll of fabric for cutting. And of course, we can use bound or unbound surfaces as required. We're not going to change those settings right now in the interest of showing you the overall workflow. But what we're going to do is we're just going to change this to put an additional number of copies. So let's just say we put 20 copies in, and there we go, 20, and just click OK here. And now we'll have to reset our marker again, and there's our 20 copies. Now we're going to run this nest, and as we run the nest, our status indicator is going to be on the right-hand side, and we can see the yield and how things are progressing along. But we're going to close out of this because one of the great features of ExactFlat is you can actually let this run in the background. You can queue it up, you can have it run overnight, and we're actually going to go back into our pattern environment, and we're going to add alignment notches for sewing. So here we just have to click the edge. We've created the edges already. And we're going to go create a notch chain. And we're going to specify a count of notches. And that's how fast it is to put notches on here. I will say that the notches, again, similar to the seams, are features which can be defined and accessed from our ExactFlat database, which does ship with the product. And they are editable and configurable. So the notches, here we're putting a standard V-notch in, but if your organization or your industry uses a particular notch type, you can configure those notches for whatever purpose you have in mind. And we do support a number of different geometries that come standard with the product as well. The benefit of having the notches and the other pattern features pulled from the database is that if you wanted to make changes, you would make changes to your notches in a very similar way. So for example, if you took this car seat and you said, it has to be 5 millimeters longer for whatever design criteria you might have. If you build your model parametrically, you could update that model, and then you could actually go in and change the notches. And if you specified a certain number of notches within the length, that would update automatically as well. So the advantage of having these features applied through a database are very, very strong. And what we're trying to do here is we're trying to apply principles that are very similar to lean manufacturing to lean design, and that would be no waste and no weighting. So here we have our pieces already notched up. Let's go back to our marker environment, and we can now see our marker. Let's go check on our nest. So our nest is run. It's compacted itself down. We are at a yield right now of approximately 75%. And we could play with this and get it up higher, but what we're going to do is just export this file. We're going to accept the nest. We're going to export this nested file. And you can see that we have a number of options in terms of layer assignments that are supported. If you want to put labels or notches or drill points or things like that on your as part of your cut file. And here we're going to export to a cutter. We do support the major cutters in the marketplace and double AMA and ASTM standards in terms of DXF files. So let's just save this one here. And let's open it up really quickly. And as we're waiting for that to open, we can zoom in here, and we can see the zoom in and see the individual pieces here. So you can see that there's our perimeter edge that will be cut. There's our notches, and here is some tagging information that came along, and that was part of the rules that we had in our initial database. This, of course, is configurable and editable, and at the user's control. So that's it. That's the workflow. For those of you who are familiar with this type of work, you know that it can take much, much, much longer. But what we're going to do now is we're going to switch gears a little bit, and we're going to close out of the nesting environment, and we're going to open up a more complicated piece here. So what we're looking at here is...
Ethan, Sham here. I just wanted to put out a polling question before we jump into the second model.
You are 1 second ahead of me, Cheyenne. That's great. So if we can put the polling question up. The polling question is, how do you currently flatten complex pieces in your design? I just want to see if the participants are using physical prototypes, sheet metal tools, or other software.
While the audience is answering that poll, I wanted to address one thing. This is a partner product to the SOLIDWORKS ecosystem. This is a third-party product that plugs into SOLIDWORKS. We've recently graduated ExactFlat from Research Associate to Solution Partner, so it integrates very well into SOLIDWORKS 2014 and 13. It is not a product that SOLIDWORKS sells. It's sold by Tri-D Technologies.
Okay, so it looks like we have a fair number of participants who are using physical prototyping methods as well as sheet metal tools. I will say that the geometry that you're looking at here, this is a steering wheel, is much more...
You need to share your screen?
Okay.
There we go.
Okay.
Thank you.
The geometry that you're looking at here is a steering wheel with much more complex non-developable surfaces. And for those of you who are not familiar with non-developable surfaces, it just represents geometry which has bends or curvature in multiple directions. So unlike, for example, a cylinder, which has a bend in one direction, this has bends in many, many directions. What we're going to do here is we're going to go into our flattener view, and we're going to show how the flattening process would be manifest on a more complicated piece. We're just going to start with the bottom piece here. So if you click on the bottom piece, we've already got a mesh created here. You can see that there's considerable strain and sag in this piece. And the black representing sag, which is about less than 0.5%, the red being stress of greater than 20%. And as our algorithms are running here, you can see that the shape is actually being deformed, the stress and sag are being eliminated. Now I'll just talk a little bit about what's happening here. So in terms of our process, what our algorithms are doing is they are first and foremost creating a mesh, and then we convert that to an analysis mesh. We have a fracture algorithm that takes each triangle in the mesh and just lays it flat. Just breaks it apart, lays it flat. And where there's gaps in the surface, after you lay those flat triangles down, it sews up those gaps. If your surface is developable, then that result should be an adequate result. If it's not developable, we'll have to go through this optimization cycle, which is what we're going through right now. And if you look down here, you can see that we're at about 60% of the way through here, and the algorithms are trying to optimize. There's really a couple things that I want to call out in terms of how we optimize. First of all, this is a product that does take into account the engineering properties like Poisson ratio and Young's modulus, as well as other characteristics. And so depending on the material, the results you get may be different. So if you're using a very stretchy material, your pattern piece may be different than if you're using a material, say, for example, a carbon fiber composite, which doesn't stretch that much. You would have a different a pattern shape at the end and a different overall perimeter geometry. Once the algorithms start, it does a search for strain and sag, and it tries to eliminate that strain and sag. And it does this through an iterative process. If it finds it, it reshapes the polygons, and we have a new candidate for a flat pattern. And after that reshaping, if it needs to go through another cycle, it'll go through another cycle. It may go through 10,000 or more cycles before it's done. So it's very similar to what happens in a manual flattening process or manual pattern making process. And here you can see we've got the flat pattern complete. It's roughly got the strain and sag where you'd expect it to be. And now it's ready for print, either plotting out on a printer or on a plotter, or cutting on a cutting table and putting on your physical prototype. So I'm going to stop there, Cheyenne, and I'm going to just open the floor to any questions that people might have. But before I do that, maybe we can put up another polling question to see what specifically people are interested in hearing more about. Is it the patterning, flattening, nesting, or all of the above?
Excellent. Thank you, Ethan. While the audience is answering the polling question, there's a few other questions that came in through the chat. One question was, how does the software tool compare with FiberSim?
Well, we're not that familiar with FiberSim, so we don't want to speak about FiberSim specifically. What we can tell you is that we understand FiberSim to be quite a bit more expensive. This was designed for industrial fabrics, composites, and technical textiles. So it really is for soft-formed materials. The algorithms that we have are trying to do a couple things. Number one is we take a look at the energy within our pattern pieces, and if you can just think about taking a piece of cloth and stretching that cloth. And when you stretch it, the cloth is it's going to want to behave like a spring and return to its original shape. When that happens, we say that there's energy in the cloth, and we're trying to get the energy to be zero so that we have a strain and sag-free piece. I can tell you that we've had tremendous success in working on complicated surfaces. So surfaces, for example, that would be for upholstered furniture, for the marine industry, boat hulls, formed metal, composite pieces. We've had tremendous success with accurate pattern fitting. So we do pride ourselves on the accuracy of our output. But as far as the differences between FiberSim, I mean, that's that's a more complicated question that we don't have an answer for right now.
That's understandable. Another question that came in, can you define symmetrical parts?
Can we define symmetrical parts?
Yes, so when the left side of your car seat is the same as the right, can you model the half of the seat?
In fact, the car seat that we showed you was modeled as half a car seat, and then it was mirrored. So yes, we can.
Okay. Another question was, how did you get to the first image of the seat with all those pattern pieces, the one that you started off with?
That was modeling. So we actually that particular one was a digitized car seat. We took a pro-based digitizer, digitized in the edge geometry, surfaced it, and then mirrored it. And so there's a number of ways that the initial geometry can be created. Because SOLIDWORKS supports a variety of inputs, a variety of file types, we often work with step or IGES files that get imported into SOLIDWORKS, laser scanned input, and digitized input as well.
There's a question about... Sorry,
just one more point there. We could, in fact, start the process in 2 dimensions. If we had a 2-dimensional version of the car seat, that means the flat patterns are ready. We could import that as well. And put on the pattern features and do the nesting as well. So it's a tool to go from 3D to 2D to the cutter, but as well from 2D to pattern engineering to the cutter as well.
There was a question about how do you handle dot and how do you handle holes in the model?
Okay, so if we just throw up the, is our screen being shown, Shyam?
No, not yet. So you may want to take control back.
Okay, so we'll take control back here. So for example, if you just want to close out of here and go into our pattern view, please. Okay, so if we look at the ExactFlat tools, we have grain lines, drills, notches. We do support SOLIDWORKS. If you wanted to do some editing of the pattern pieces, you can do editing of the pattern pieces as well. So if the darts can either be modeled in 3D or they can be put later on in 2D.
Okay, we will put on one more polling question for the audience. While that is being answered, we can answer a few more questions from the audience. Can you use this model, this program for inflatable boats?
Yes, we can. In fact, we have used this program for inflatable boats, inflatable slides for aircraft, inflatables like hot air balloons, tethered aerostats, and a whole host of other inflatable objects, inflatable lifting devices, rubber bladders that would be inside tanks and things like that. So it is absolutely, and the engineering characteristics of the rubber or the technical textile would just have to be associated to the material, and then it's perfectly fine for that type of material.
Okay. We'll take 2 more questions at the end. There was a question, a lot of questions about materials. What kind of materials can you handle?
Well, we have a number of algorithms that support both anisotropic and isotropic and orthotropic materials as well. So if you're talking about what kind of materials can we handle from a flattening process, the programs and the algorithms were designed for flexible materials. And we do have companies using it for complex metal forming, like for ship hulls and things like that. But any range of materials that you have the engineering characteristics for, we do support. We will say that there are other criteria that have to be put in place if you're working on materials that are under very, very high constant tension. Say, for example, architectural roofing or things like that. There's other considerations that you have to take into account as you're making your pattern pieces that we do not support. But if it's standard flexible materials for soft goods, we handle them all.
Okay, I'll take one last question. Let's see, I've got a lot of questions to choose from. The question is, I'm building a safety harness. Can the software use body models or mannequins?
Well, in fact, we do support that. We've actually done some work with companies doing body scans and modeling on top of those body scans. So the body scan would be an input that would help the design process and the modeling process. And the body harnesses or the clothing or the whatever the element is can be modeled on top of these things. Because SOLIDWORKS supports parametric addition of features. If you have a body which is, say, tall and thin versus short and fat, we can support that as well. And we do have some examples of bulletproof vests, for example, being modeled on top of 3D avatar and than changing the size. So if that's the type of industry that you're looking at, then we'd certainly support that. The other thing I'll say about harnesses, we do a lot of work with harnesses. We've done some work with some space agencies on harnesses that they would build and coverings for vehicles that have equipment that needs to be protected, both insulation on the materials inside and coverings on the outside. So we're well capable of handling that class of material.
Excellent. Thank you, Ethan. There's a lot more questions. So for the audience, what we will do is we will collect these questions and submit it to ExactFlat. Ethan, if you could create an FAQ document answering these questions, we will make it available to the audience. We just have too many questions to go from.
All right, so we would be happy to do that. And if anyone has any questions immediately, I would just direct them to our website, which is ExactFlat.com. And we have a video page, ExactFlat.com/videos, where there's a number of examples that I think can answer some of the questions that I see here. And we would encourage anybody who's got an interest to reach out. And we thank you very much for your time. And thank you, Shyam.
Thank you, Ethan. Closing remarks, we have a SolidWorks offer running right now. It's a buy two, get one free. So you could buy any two of the SolidWorks modules that you see on screen here and get the third one for free. This is running till the end of December 15th. And you can get to the link that you see here, solidworks.com/2013_mix_and_match for more information. Thank you for your time. This will be recorded and will be made available to you by the end of the week. Thank you, everybody.